All right, now we're going to look at some energy diagrams, and we're going to go over this vocabulary again. So let's remember the heat of the reaction, known as the enthalpy, or our delta H, is the amount of energy released or absorbed as heat during a chemical reaction. Okay, delta means change, and then H is going to be heat. So when I ask you to calculate the delta H, I'm asking you to calculate the change in heat. Okay, another vocabulary word, this one we haven't seen though. All chemical reactions, even exothermic reactions, need a certain amount of energy to get started, and this energy is called activation energy. And we're going to see this, EA. So that's going to be the variable for activation energy. And this is going to be in the form of heat, like I need to put it, this reaction on the Bunsen burner or the hot plate to get it going. Okay, so we're going to calculate delta H and activation energy for these. All right, let's recall when we looked at potential energy diagrams earlier, we said an endothermic reaction is uphill, and an exothermic reaction will go downhill. Okay, because we're gaining heat, losing heat. Okay, so let's look at this potential diagram right here. Is this forward reaction endo or exo? So going forward, we're only doing forward reactions. Is this endo or exo? Well, let's look at it. Does this graph go uphill or is it going downhill? Well, here are my reactants, A and B, and here are my products. Notice my products are at a lower potential energy value than my reactant. So it's going downhill, so we're saying this is an exothermic reaction. Okay, now we're going to determine the heat of the reaction, or the delta H, for the forward reaction. So how do I do that? Okay, it is the difference between the products and the reactants. So remember, C and D are the products, A and B are the reactants. So it is the difference between, you can see that little dotted line, the products and the reactants. And the products are at 20 kilojoules of energy. So the sum of the change in heat for the product, so that's 20 kilojoules of energy. And we're going to subtract the sum of the change in heat for the reactants, which we can see that is at 40. And we just subtract. So 40 minus 20 gives us negative 20 kilojoules of energy, which makes sense, right? Because the delta H for an exothermic reaction is negative, right? So that would make sense if this is an exothermic reaction. Okay, the other thing you're going to calculate on these is you're going to calculate the activation energy. Okay, how much heat do I need to add to this reaction to make it go forward? So what we do is we take the reactants, the energy of the reactants, okay, A and B, and the energy at the top of the hill. So that's at 100. So top of the hill minus the energy, I'm going to put kilojoules there, minus the energy of my reactants, and I get positive 60 kilojoules of energy. Okay, activation energy is always positive. So don't do it the other way around, okay? So look at 6, 7, and 8. We're going to answer these same types of questions using this, okay? Just remember, we're going to subtract on both of these. Just figure out where your reactants and your products are, and then calculate. Then on the back page, we're doing the same thing for 9, 10, and 11. When you get to number 12 through 15, though, we're going to figure out which one of these letters represents the delta H. So is it A? Is it B, C, or D? Which letter represents the activation energy? All right, label your reactants and products just like I did right here, reactants and products. And then is it endo, exo? And then down here, we're going to do the same thing. Label what number 3 represents. Is that your activation energy or your delta H? Is number 4 your activation energy or your delta H? Label the reactants and products, and then circle, is it endo or exo? Okay, let me know if you have any questions.